Hello, it's Keith here, and this is lesson 4 of my SuperH assembly programming tutorials. We're going to be going through some more essential programming commands today. We're going to be going through logical operations, signs and shifts. Now, signs is converting signs and things like that, and shifts is bit shifting operations, logical shifts, rotations, stuff like that. All the stuff you're pretty certain to need in basically all kinds of programming, really. So we've got another piece of example code. We're going to see all of those in action. Let's go over to our code. Let's get straight into it. Okay, so the file we're going to be looking at today is lesson4.asm, and as before, we've got a jump block at the start of our code, and this will branch to the various sections of our program. Let's get that out of the way. We don't want to see the build results there. So let's fire it up, and let's start off with logical operations. Now, what are logical operations? Well, these might be something you're familiar with if you've ever done any sort of beginner's hardware stuff, because there's sort of various kinds of gates that have the same kind of name. Also, various kinds of programming, you might have come across them, but if you'd only done things like BASIC, then there's a good chance you won't have. Anyway, they're all pretty straightforward, and if you think about them in the right terms, they're very easy to understand. So, as always, we're loading some test values into some registers here, and we're picking some specific test values that are going to have very clear results here, and then we're going to perform some logical operations. Now, these logical operations use a source parameter and a destination, and the logical operation is performed between the two parameters, and then the result is stored in the destination. Now, the source parameter can either be an immediate, and the destination can be R0, or the source can be any register and the destination can be any register. Now, in this case, we've got some test parameters here, and we are loading the value in R4 here into R0 and R1, and then we are going to perform the operation with either the immediate F0 or the value in R3, which is this very unusual value here, and we will see why in a moment. Now, logical operations work at the bit level. So, of course, each of these values, these are shown as hexadecimal, but each of these values has a value in bits, and a value of a single 0 nibble in hexadecimal is 40 bits, and a nibble of F is for 1 bit, and so on and so forth. Now, you can see the values in binary using your calculator if you need, but what we're going to be doing today is logical operations which work at the bit level. And so when we do the command AND R3, R1, what this is saying is if one of the bits in R3 and the bit in R1 are both 1 at the same position, then the bit in the same position in the destination, which is R1 as well, will also be 1. But if the bit in either of those is not 1, because it's AND, if this and this are true, then the result is true. Otherwise, the result is false. Now, that sounds a little bit confusing, but if we see it in the code, we will understand exactly what this is doing. So our results are going to be in R0 and R1. So let's take a look at R0 and R1 here. So in both cases, we've used the test value 1, 2, 3, 4, 5, 6, 7, 8, and we've performed the operation on those values. Now, when we have performed AND with F0, you will see all of the bits, except from the second to last nibble there, have been reset to 0, and the value in that nibble there has retained the value 7. Now, why has that happened? Well, because all of the bits in the test value, because we only had a 1 byte value, all of these bits here, when that AND was performed, the one of the values was all 0 bits, so they were all lost and reset back to 0. The bits in this nibble were also reset to 0. However, the bits in this value were retained because they were ANDed with a value F there, which is all bit 1. That's a nibble with 4 bit 1s in it. So that is why that part there has been retained, but all the other parts have been cleared by that AND operation. Now, the second one we did is we took 1, 2, 3, 4, 5, 6, 7, 8, and we ANDed with FF77 quadruple 0. Now, that has resulted in the value 1, 2, 3, 4, 0, 0, 0, 0. And again, that's because when the AND was performed, these 4 bits, when ANDed with these bits 0 here, the result was always 0 because both of the bits would have to be 1 for a 1 to be returned. Now, the 1, 2, 3, 4 have been retained because the matching bits in this part are actually all 1 bits there. If we get our calculator up, if we do the value 1, 2, 3, 4 here, you will see in binary, you will see you get this value here. And then if we do the value FF77, you can see actually only 2 of the bits in here have been reset to would have been cleared by this AND operation, and those bits were not set in the original value, so that part of the original value has been retained. But if we changed this test example to a different value, obviously we would get a different result. So if I change this from FF77 to FF11 and I run this again, well, now the value 1234 has been changed to 1210 because the matching bits, only the bottom bit of these 2 nibbles here will have been retained by that AND. Now, as I say, if you look at the bits and you think how they've actually been calculated, all of this makes a lot of sense. But if you're a little bit confused, then there's a very easy way to think of an AND command. An AND command will basically clear the bits where a bit in the passed parameter is 0. So in the case of this F0, which is effectively 6 zeros F0, all of those 0 bits were cleared in the result. And the same was true of our value here. All of these bits were set to 0. So as I say, the easiest way to think of an AND is that it will keep the bits where bits are 1 and where nibble is F effectively, and it will clear the bits where they're 0. And so that's what the AND command will do. Now, another one is the OR command, and the OR command is basically opposite to the AND command. AND command will say where a bit in both parameters is 1, then the result is 0. The OR command, you can maybe guess, it says when the bit is 1 in either of the 2 parameters, in the source or the destination, the result in the destination will be 1. And so if we think of the AND command as being basically a command that retains the bits in some positions and clears them to 0 in others, the OR command is effectively a command that retains the bits in some positions, the bits where the parameter had a value of 0, and it sets them in the other ones, the bits where the parameter is 1. So let's take a look what this does. So once again, we start with our value 1, 2, 3, 4, 5, 6, 7, 8. Now our first command here is using the value F0, and of course the other bits above the F there, the 6 bits of the 32-bit value that would be effectively used will also be 0. And so you can see here that in this case the 1, 2, 3, 4, 5, 6 has been left unchanged, as had the 8, but the 7 has been changed to an F because, as I say, if in the case that the bits in either of the source parameters is 1, the result will be 1. And so basically that F has been passed through to here. And in the same way, the FF77 quadruple 0 that we ORed with our test parameter here, that has also been pushed through, and the top bits now are FF77, and then the 5, 6, 7, 8 is unchanged because the bottom bits were 0. And so that's how the bits are changed by the OR command. Now that's AND and OR, as I say, great for setting or clearing bits in a parameter. XOR is a slightly different one. This is effectively, it's known as an exclusive OR, but the way it's easiest explained is it flips the bits. Where the bit in the parameter is 1, the bit in the destination will be inverted, and where the bit in the parameter is 0, the bit in the destination will be unchanged. Now, in the case of our example here, we started with our values 1, 2, 3, 4, 5, 6, 7, 8. And so the F0 here, when performed with an XOR command, that would be referred to as EOR on some systems. The 7 was actually flipped to an 8. Now, why did that happen? Well, if we get our calculator up here and we put in hexadecimal and we look at a nice simple value here, we'll just delete that and we put in 87, you can see here, this is the value 7 in binary here, and that there is the value 8 in binary, and you can see that the bits are effectively flipped in that 4-bit nibble. And so when we perform our XOR command with a single nibble set to bit 1s, all of that nibble will be changed and inverted, and so our 7 gets flipped to an 8 in that case, and so that's why that has happened there. Now the same has also happened to our 1, 2, 3, 4 here. We XORed that with the value FF77, and so that has become ED43 here. And the 5, 6, 7, 8 has been unchanged, and that's because the bottom bits here were 0 in the parameter we XORed. Now XOR is an inversion operation, so if we perform a second XOR after the first one, if I just change the code here, And if I now run this again, you will see that we've got our values here as we just saw, but then after the second XOR, because it's an inversion operation, if we use the same parameter to perform the inversion, the result will be the same as we started, which is completely logical, but just to add some clarity to the fact that that is what that is doing. So those are our primary commands. Those are very common that you will use. You often use these kind of commands with regards to filtering out values. Let's say, for example, I've loaded in a value from a joystick and I only want the fire buttons. I want to get rid of the other bits. Well, I can use an AND to do that, clear the bits that I'm not interested in. I just use the AND mask and select have bit ones in the parameter that I use the AND with to keep the bits that I want to look at. That's one option. Now, let's suppose another option. Now, I'm often working multi-platform, so I'm converting systems so that they all output the same values. Let's say I've got a system that has a joystick with 8 buttons, but then I've got a system that has a joystick with just 4 buttons. And I need to set the bits to 1 for the buttons that don't exist so that the code works in the same way. Often bits are set to 1 when a button is depressed, and when it's pressed it goes to 0, you see. Now, I could use the OR command to do that, because that will set the unused bits with a mask accordingly. So that is something I might want to do. That's how I often use that command. Now, what about XOR? Well, often, as I say, joysticks will actually set bits to 1 when the button is not pressed, and then it will go to 0 when it is pressed. However, every so often you get a system where that's the opposite, and you need to, if you're working in a multi-platform code making a driver that works in the same way on all systems, you're going to need to flip that the other way. And that is often what you will use your XOR for. So XOR is for converting values from 1 to 0 if you need them the opposite way around, or is for setting bits to 1 where they may or may not be 1 before, and is for setting bits to 0 or effectively retaining only certain bits from a parameter. All very useful commands. Now, there may be times where we want to test a value in a parameter and see what its value is, or see what just some of the bits are, but we don't actually want to change the value itself. Like, take my joystick example, say we just want to check the bit that corresponds to up, but we want to check the other bits later on, so we don't want to change the value in our register, we just want to test one of those bits. Well, that is what the TST command does. This effectively sets the T flag if the result of the comparison and the comparison is effectively an AND. If the result is 0, then the T flag will be set to 1, otherwise it will be set to 0. And so, as I say, if you think of my joystick example where we've got like a single bit, let's say bit 0 for example, if bit 0 was the up button and we wanted to test if the up button was pressed, we could do a test command with a mask parameter of just the bit 1 set, and if that result is 0, if our joystick goes to 0 when the button is down, then we will know that that button was pressed. Now, if we just run this here, we will see how this works. So here we've performed a test with R3 and R1 here. Now, R3 contains the value FF77 quadruple 0, and in this case R1 contains the value 5678. Now, if we effectively ANDed these two values together, the result would be 0. So in this case, this test has set the T flag to 1, and so that is shown a T here. But you should notice that the values R3 and R1 are unchanged here, because as I say, that is the only difference between this command and AND. The flags are set the same, but the registers are unchanged. So that is what's happened when we've done this test here. Now, if I just close that down, and if I disable this line and I run again, we're going to perform a different test. This time we're going to test this value here with the value F0. Now, the F0, of course, is represented there. So if we effectively ANDed these two together, we would get a value that's non-zero. And so in that case, the T flag is clear. And so this line has shown an F there because that's representing the T flag. So, as I say, those can be used to effectively test a set of bits. And say a great example of when you would use this is if you want to check if a certain bit is, or a certain combination of bits is set or clear within one of your registers or one of your memory mapped pieces of hardware. And often on 8-bit systems and things, you will want to test if a value is 0, and test commands are great for doing that as well. So there we go. Now, here we've used registers and we've used immediate values. Now, one interesting thing that I didn't point out specifically here, but I mentioned it before, is that the immediate values are unsigned here for these 8-bit immediates, which is a bit of an exception because usually they will be signed extended, but it doesn't really necessarily make sense to sign extend for logical operations. There would be benefits to it, but as I say, you can understand why they've chosen to do that. One other thing you can do though is you can use the global base register. Now the global base register I believe is designed for peripheral data, but we can just use it with regular memory here. So what we've done is we've loaded test address into the global base register here, and test address is just simply some values here. And then what we're going to do is we are going to mess with some of them. So we've got these values here and we're going to just mess with a few of them here. So what we've done here is we've ANDed F0 to the global base register, and we've set R0 to an offset of 0. It's got to be R0 that's used as an offset here, but basically we've done an AND there, and so you can see that first value has had its bottom nibble reset to 0. Then we've done an OR here, and you can see that value has had its top nibble set to F here because of that OR. Then we've done an XOR, and so you can see that nibble has had its that byte has had its top nibble inverted to E there. And then we've done a test here, and so we've effectively tested that value there, and in that case that value was 0F, and so when we've tested that with F0, the result is effectively 0, and so the true flag, the T flag, has been set there by that test command. So as I say, you know, there's a wide variety of options we've got there. Not something you may need, but definitely worth me quickly mentioning. So yeah, that's an introduction to logical operations. If you don't understand them, don't worry too much about it at this point, because you're going to come across times when you need them, and a lot of these commands, when you actually use them, you will start to understand and need them. You will start to understand what they are, because you will start thinking, hang on a minute, I need to clear some bits. What command do I use for that? Well, it's going to be AND. Hey, I need to set some bits. What do I use for that? It's going to be OR. Hey, I need to flip some bits. What do I use for that? It's going to be XOR. So as I say, you will very quickly start to understand them. Another thing that you will need an awful lot is shifting commands. Now, in the example of my joystick earlier, you will often, if you're reading data from a joystick, sometimes the bits will be in the wrong positions and you need to shift them around. Another very important reason you want to do bit shifting, not necessarily so much on 32-bit systems, but on 8-bit systems, is because it's a very simple way of doing multiplication and division. When we shift all of the bits in a register to the left, we're effectively doubling the value in that register. When we shift them to the right by a single bit, that is, we effectively halve the value in the register. And so on 8-bit systems with no multiply and divide commands and limited amounts of performance, that's an invaluable way of performing simple multiplication and division. So we have commands to do that, and that's what we're going to look at now. Now, the problem, shifting left is always fine. We can just shift the bits to the left. Any new bits that are introduced by a shift command will be 0, and that will work fine for signed or unsigned numbers. It will double the number's value every time. But when we shift to the right, if we add a 0 bit to the right-hand side and it was a negative number, that will flip the sign of the value, and it will convert a low number to a quite high number when we shifted to the right. So we wouldn't want to do that for a signed number. What we actually want to do for signed number is shift all the bits to the right and then keep whatever bit was at the top before. So if there was a bit 1 at the top before, that will mean that it was a negative number, and so when we shift all the bits, we want to keep a 1 bit at the top, and that will keep the sign correct. However, if we did that for an unsigned very high number, that would ruin the unsigned number. So we need different commands for right shifts for signed and unsigned numbers, and so we do indeed have them. We have shift arithmetic and shift logical. Now here we're using shift arithmetic left and shift logical left. We're doing R1 with the arithmetic and R0 with the logical, and our values are the same in both cases. Now that top nibble of 8 is effectively a negative number if we treat this as signed, and if we treat it as unsigned, it means it's a quite high unsigned number. So when we're shifting to the right, that's going to get important. Anyway, here are our shifts to the left. Now, we're shifting 1 bit at a time, and so we're looking at these in hexadecimal values because the 32 bits would be far too long to show them as binary. But effectively, if we shift 4 times, we're effectively shifting 1 nibble, which is 1 hexadecimal digit. So you can see here we've got 8, 7, 6, 5, 4, 3, 2, 1 here, but then after 4 shifts, we've shifted effectively 1 whole nibble. So we've got 7, 6, 5, 4, 3, 2, 1, 0. All the new bits were 0 there. And after another 4, we've got 6, 5, 4, 3, 2, 1, 0, 0. So with this shift logical, all the new bits were introduced on the right hand side as 0. The shift arithmetic has actually done the exact same thing here. So we've got the same result in both cases. So effectively, these are actually, to all intents and purposes, the exact same command in this case. So we kind of don't need to worry about which one we're using when we're shifting left, because the sign isn't negatively affected, and the only time the sign is affected is if we're actually multiplying the number up so much that the resulting value can't be stored in a 32-bit number, which is another problem. But there's nothing we can do about it. There's no special command we can use to solve that unless we're using pairs of registers to simulate 64-bit values. So that's shifts to the left, which, as I say, will effectively double a number. What about shifts to the right? So we're shifting for arithmetic, meaning signed numbers are 0, and we're shifting logically to the right for unsigned numbers here in R1. So here's the value we've ended up with in our test here after the previous set, and so we're shifting arithmetic to the right here, and so you can see after 4 shifts, the C864200 here has become FC86420 here, and by the end it's FFCA8642. Now, why has that happened? Well, the F's have been introduced here because the top nibble of C there had a top bit of 1 because it was effectively a negative number here, and so introducing new bits of 1 here that have become nibbles of F means that that sign has been retained as the bits are shifted to the right and the value is effectively halved. So that is our arithmetic shifts. Here are our logical shifts, and you can see here we start with the same value, but as we shift to the right, the new bits that are introduced are actually bits 0 here. And that is because this is an unsigned number, and so when we're halving the number, we need to make sure that the new bit's introduced to 0. And so we're effectively halving the number and treating it as unsigned there. And so while it didn't matter which of these commands we used for shifting to the left, it definitely matters which of these commands we use when we're shifting to the right. Now, one important thing to point out is that the fact that the new bits on the left hand side with the shift arithmetic were all 1 was simply because that was what was required to retain the sign of the original number. Here I've reset the test values 87654321. The top bit of that nibble 8 is a 1 here. So again, new bits that are introduced are 1s, meaning that the new nibbles are F's here. But if I change this and I change this to a value of 1 here, and I run again, well, that nibble has a top bit of 0, so this is a positive number effectively. And so when we shift to the right now, all the new bits that are introduced are 0. So it looks like the result is the same as if we'd have used the logical shift. Well, that would be true, but only because this number is relatively low. And so the arithmetic shift does what is appropriate to retain the sign of the number. The logical shift always adds bits 0s to the most significant bit as the shifts are performed. So there we go. So that's the difference between logical and arithmetic shifts. It's quite possible on 32-bit you're always going to be working signed numbers. In 8-bit mathematics and things, you often are working in unsigned numbers unless there's a very special case you need to be signed. But as I say, it's just important you make sure you understand the difference between the two and that you are using the correct command for your signed or unsigned number. Now, there are a few special case commands with the SuperH. These commands always work a single bit at a time. So these commands always shift a single bit, these parameters, but there will be cases where you actually want to shift more bits in one go. Maybe you want to shift 4 bits or 8 bits or even 7 bits. There will be times you want to shift certain amounts. Now, we have a limited number of options here. We've got those commands you saw before to shift a single bit each time, but we do have some special commands to either shift 2 bits, 8 bits or 16 bits, and we can do this with a logical left shift or a logical right shift here. And so you can see we've done them here. We've got our starting test value here, and we've shifted it logically, effectively 2 bits, converting those 1s to 4s, and then we've shifted 8 bits, effectively moving them 2 nibbles, 1 byte, and then we've shifted them 16 bits, effectively moving them another 4 nibbles, 2 bytes, and that's a result of these commands here. Now here we've shifted them to the right here, and you can see the result again. Now we've only got options for 2, 8 or 16. So if you wanted to shift 9, then you'd have to use a combination of shift left logical 8 and then a single shift left logical here. So you'd have to combine multiple commands. Really, these are just to stop you having to have a series of 16 shift commands to get to the position you want. So as I say, these are really just to speed up the operation of shifting. Now, the other thing is these only exist for logical shifts, and these are really designed for you to, I think, to move values around within registers, as I've said before. If you're reading in from a piece of hardware and a value is in the top byte and you need to move it to the bottom byte, well, you would want to use a combination of a shift logical to the right 16 plus a shift logical to the right of 8. It's far more convenient to do that than to have a whole bunch of these shifts in a loop. So you'd waste a lot of processing power there. So those are certainly options available to you. Now, that's how we can do shifts, but there is another thing that is definitely related to shifting. As I say, shifting is often about halving and doubling, but there is another kind of command which is a rotate. Now, whereas when we shift values, data that is pushed out of the registers effectively is gone, it doesn't come back. Rotates are moving the values around within the registers themselves, and so when we rotate and value bits are pushed out of a register, they actually come back in on the other side. So what we're going to do here is we're going to use some test values here, and we're going to rotate them to the left, and then we're going to rotate them to the right, and let's see the result. So we start with the value 4, lots of zeros and then a 4, and we're going to rotate that to the left once here. Now, when we rotate that one bit, the 4 becomes an 8, so we end up with 8, lots of zeros and then an 8. We then shift another bit, and the 8, the top bit 1 there in that nibble of 8, then gets pushed out the left hand side and returns back on the right hand side. So that 8, lots of zeros, 8 becomes a 1, 1, which then becomes a 2, 2, then becomes a 4, 4, and then becomes an 8, 8. And if we rotated this enough times, we would actually end up with the exact same starting value that we began with, because no data is being lost and no data is being introduced. It's but just being rotated around within the register. And we can see this as well with our value of 8765431 here. 8765431. Well, if we take a little look at here, we can see 76543218. And by the end, 65432187. The bits are being rotated to the left, but as they're pushed out the far left, they're reintroduced on the far right. It just keeps rotating around. And so that's rotations to the left, and then we can do rotations to the right as well. So we start with our 880 here, that is the final state after the last operation here, and then we're rotating that here, and lo and behold, at the end here, we end up with the exact same value we started with, because if we rotate to the left 8 times and then we rotate to the right 8 times, we end up with the same value we started with, because as I say, nothing's lost and nothing's introduced. And you can see that the same is true here, because we're rotating all the way until we end up with the value that we started with. Now, rotation is very handy for times when you've got data, but it's not quite in the right format for what you want to do today. One example would be graphics data. Some of the systems I work with, I'm using the same bitmap data on 2 systems, but maybe the pixel data for the screen memory is actually oriented in a different way. If you've got 2 pixels in a byte, maybe this one is the left pixel and this one's the right pixel. On another system, they may be the other way around, and if I don't want to convert the source data, I can just rotate the data 4 bits and it pushes the 2 pixels, swapping them around within the byte. And that's the kind of thing you'll do. I say again with my joystick example, maybe one system has the up, down, left, right in the low nibble and the fire buttons in the high nibble. The other one may have them swapped around, and I may want to flip those around accordingly, and rotation is a very good way of doing that. So those are definitely worth considering. Now, I was specific that those commands don't introduce anything new to the byte and don't remove anything. There are some alternate versions that use the T flag as a carry. Now, what does a carry mean? Well, when a bit is pushed out of the left-hand side, in the previous example, it immediately returned on the right-hand side, and vice versa when we're shifting to the right. Now, in the case of a carry, what happens is the bit that is pushed out is pushed into the carry flag, which is in this case the T flag. And then when a bit is pushed in, the previous value of the T flag is pushed into the register. Now, what is this for? Well, the most common case you might want to use this for is for combining 2 32-bit registers into one 64-bit value. When we shifted to the left, we were effectively doubling a value in a register, but if we were at a very high value that was already at the limit of a 32-bit value, shifting it to the left one bit won't double it because we will be losing bits. If we combine two registers and we transfer data from the low part to the high part register via the T flag, we're effectively using two registers as a 64-bit pair. Another purpose you may want to do this for is if you wanted to artificially introduce a new bit, like maybe you want to shift all the bits to the left and you want to force a bit 1 into the bottom value. Well, you could do that with the OR command, but you could also just set the T flag and then rotate it in. In this case, we're clearing the T flag and rotating 0 bits in, and that's because we're going to be effectively simulating the doubling and halving of an unsigned number. So we're going to use R0 and R1 as a 64-bit pair. R0 is going to be the high part and R1 is going to be the low part, and that's just because of the convenience layout of the screen here. So our start low part value is 8765431, and you can see that in R1 here, and the high part is of course 0. Now we're going to clear the T flag and we're going to rotate to the left, and that's effectively putting a 0 into the bottom part of R1 here. We're then going to rotate R1. The T flag will be set with anything that was pushed out of R1. We're then going to rotate into R0, and if a bit 1 was pushed out of R1, it will be rotated into R0 here. And so you can see as we're repeatedly rotating these values here, bits are being pushed out via the T flag and they're being transferred into this value here. Now you can't see the T flag here because it's already been changed by the time the point that dump is being done, but you can see the T flag is being set because those values are being effectively transferred here. So that's rotations to the left, effectively doubling a 64-bit number in this case. We can also rotate to the right here via the K as well, the T flag. And so you can see here we're doing that, and once again, because the bits are being transferred back through the T flag, the end result is exactly the same as the start, because that has worked just fine. Now of course we could, if we wanted to, we could set the T flag here, and now if for some reason we wanted to do this, we're now effectively forcing bit 1s into the low part of our values because we're setting the T flag each time and then rotating that T flag into the low part. Doesn't make sense for doubling a number, but as I say, sometimes you might want to artificially introduce a series of bits into a register. Maybe you're reading in your joystick directions up, down, left, right, 1 bit at a time, and you're storing them in a build-up, so you are reading in your T flag from your hardware and then you're rotating it into your register that you're using to remember all the previous bits. Not necessarily going to happen so much on 32-bit systems, but that's something that's quite common on 8-bit systems. Often you get your directions and things a single bit at a time, and you have to rotate them into some kind of value that you're building up. So again, another reason you might want to use this. So that's shifts and rotations. As I say, very useful commands, if not just for multiplying and dividing numbers, for working with data and manipulating it into the format you want. We're now going to continue with some of the commands that I feel it's as good a time as any to discuss. Now what we're going to look at now is sign extending commands. Now there may be times where we've loaded in a value of a small size and we now want to actually convert it to a larger size. So maybe we've got a byte value and we need to now convert that to 32 bits, or maybe we've got a word value and we need to convert that. And we've got extend sign commands to do that. So we've loaded some test values here, and these values are 32 bits, but we're going to imagine that maybe only part of them is actually relevant and we need to actually convert them. So what we're going to do is we're going to take the value in R0 and we're going to extend it, treating it as a byte, and sign extend it to 32 bits in R3. And then we're going to take the value in R1 and we're going to extend that as a word into R4. So let's take a look at what has happened here. So we've got the value 1, 2, 3, 4 FEDC here, and we've got that in both cases. And when we assign extend that as a byte, you can see that the bottom byte DC has been retained. Now the top bit of that D nibble is 1, so all of the extra bits here, when it's been sign extended, have been set to 1 here. When this is a word, we've got this FEDC word at the bottom here. So when that 16-bit value is sign extended, the F of course has a top bit of 1, so that is sign extended, and all the extra 16 bits there of the 32-bit value have been set to 1 there. Now that's sign extending a signed number. We can also extend an unsigned number, which is effectively going to set the top bits to 0. This also is known as 0 extending. And so you can see here, even though we had the same values there, these are being sign extended as unsigned numbers. So that is something you may want to do as well. And then finally, just for completion, we're going to show the same commands for the sine numbers just being performed with values that have a top bit of 0, so effectively positive numbers. So here we've got a byte that is a top bit of 0, and so when that's sine extended, the result is all the bits are set to 0. It's similar to that, but of course, as I say, this isn't setting the new bits to 0. This is setting the new bits to whatever the top bit, previous top bit was. So there it was a 0, and here for this 16-bit value, that is also 0. So that top 16-bit half has been set to 0 as well. So there we go. So that's how we can sine extend values that we have loaded into our registers and we now need to convert. And then finally, just for completeness, we are going to look at negate and not. Now, we looked at the XOR command, which was an inversion command that we could specify a mask for. Now, negate and not are similar, and we're going to take a look at these now. Now, negation is effectively converting a positive number to a negative number. Now, the way that this is actually performed if you don't have a negate command is what you effectively do is you flip all of the bits in your register and then you add 1. That's just the way that hexadecimal numbers work. Now, we've actually got a command that's not. Now, this is effectively the same as doing an XOR of a destination with a parameter where all of the bits are 1. And so what we're doing here is we're taking the value in R0 and we're flipping all the bits and storing the result in R0 and also R1 here. Now, why are we doing not and negate at the same time? Well, as I say, basically the difference is that if we flip all the bits, we will get of 1, 2, 3, we will get this value here. If we flip all the bits and add 1, then we get this value here. And as I say, this is effectively the negative number hexadecimal representation of -1, 2, 3. So I'm showing the not value here just so you can clearly see that it is effectively the same as flipping all the bits and adding 1. Because if you add 1 to C, you get D. That's why that value has been achieved there. We're doing something a little bit extra though, because maybe we have a negative number, but we want to actually negate a 64-bit pair. We would actually need to continue the sign from the previous register in that case. So if this value became negative, we would need to convert the second part accordingly. And so when we've negated this using neg, we've negated this using neg C, and you can see it's effectively flipped all the bits of that top part there. But suppose we wanted to negate a different value. If we've got the value 1, 2, 3 and we do use neg C, this will correctly convert the 64-bit value accordingly. But what if the value we were wanting to negate was actually 0? Well, if we do this now, well, if we use neg C, this will effectively carry on from the lower part of the register. So when the bottom part of the register is 0, it will leave the high part unchanged because we don't want to set the top bits to 1 if the bottom part was 0. And so neg C can be used to negate a pair. If we just negated both parts independently, in this case both parts would be 0, but if we set this low part to -1, but if we set this low part to 1, 3, then this would effectively leave the high part unchanged, so it wouldn't correctly negate that high part so that we had a valid negative value. So there we go. So as I say, a variety of commands there. Some you're going to need and some you're not. As I say, please go to my website and download the source code, the build scripts, and try it all out yourself. That's the point of this. The whole intent is that you can actually try them out and learn how they work through examples. So go ahead and have a go with them. We've got one last lesson coming though, so please stick around. We've got one finish off lesson where we're going to do the multiplication commands and things like that. We're going to learn about the final few commands and some other stuff relating to carries and things. So hopefully you'll stick around for that. Anyway, I hope you've enjoyed what you've seen today. Thanks for watching and goodbye.